Today's lesson is going to be about parent functions and transforming parent functions. So be sure that you're using headphones so you can focus, and you'll probably need to pause throughout the video to write various things down. So take all the time you need to go back and understand this information. So the first thing we're going to do is we're going to go through some main parent functions. Remember, parent functions are the most basic type of function for certain types of equations. So we're going to start off one of the most basic ones, one that we're familiar with, the linear parent function. And as you can see here, the linear parent function, which we've talked about before, has the equation of y equals x. It has a slope of 1 and it has a y-intercept 0. We don't see those there because it's implied in the equation. The general form we recognize as f of x equals ax plus b, or you may also know it as mx plus b. I prefer personally to use ax, or a for slope, as you'll see why here in a minute. So when talking about the domain and range, there are different ways in which you can show it. We have what's known as interval notation, inequality notation, and set notation. So we'll start off with interval notation. Simply a line, its domain, it goes forever to the left and it goes forever to the right. So we say that we use this parentheses for the domain and say it's going to negative infinity and positive infinity. And we use these parentheses to show that it can't actually equal infinity because there's always going to be one more when you're talking about infinity. The same can be said about the range, negative infinity to positive infinity. Now, inequality notation uses these compound inequalities, which you've seen before. So basically we're saying that x is larger than negative infinity. It's not equal to, but it's also less than infinity. Again, you can't equal infinity, so we use those inequality signs, and x is in the center there. So our range, we do the same thing. Y is going to be greater than negative infinity, but less than positive infinity. Now, set notation, this is where we use our curly bracket thing, and the way that you read this is we would say that x, and then this little bar here is such that, and that little e looking thing means that is a set of, and then this r thing means all real numbers. Okay, so x is such that it is a set of all real numbers. Now the way you can write that r by hand is just like do a double bar, I guess, in the back, and that would be an easy way of writing all real numbers. So y for our range is a set of all real numbers. So let's take a look at some more. The next one is quadratic, another one I'm sure you've seen before. And the parent function is y equals x squared, and it has a vertex, and that vertex is located here at 0, 0, aka the origin. This is quadratic. Now the general form of this, and we're going to go into more detail about this later, is f of x is equal to a, so we saw a in linear, now we see a here, x minus h quantity squared plus k. Alright, so we see some two new variables, a minus h and a k. Now let's look at the domain and range when in our various notations. So let's start off with the interval notation. With the interval notation, we see that, well, the domain can be everything, so just like linear, negative infinity to positive infinity. But the range here, see, since our graph does not go down at all, it's just going up, we say that the range, the lowest it gets here is the origin at 0 on the y. So we put 0 as the lowest point. Now the bracket means that it can actually equal 0. okay, whereas a parentheses means it doesn't really equal. Kind of like a solid dot on a number line means it equals 2, but a hollow dot means that it doesn't actually equal 2. So it's the same idea but different symbols for it. So here we say it's actually equal to 0, but goes to positive infinity. So x here, just like on the linear, negative infinity, positive infinity. The y in our inequality notation can actually equal 0. It's greater than or equal to 0, so it's y values that are larger than that going up, but it's going to be less than infinity because you can never equal infinity or be larger than that. So our set notation, again like linear, x is such that it is a set of all real numbers, and for our range, y is a set or y is such that y is greater than or equal to 0. So we don't, in our set notation, we don't need to use the compound inequality. We just say, hey, it's greater than or equal to. So it's just a different way of writing it. But you should be familiar with all three different notations. Now, let's take a look at a square root. The square root parent function. Notice that equation is y equals the square root of x, and this has a point, and then it goes this way. Note the arrow. Okay, now if you don't have an arrow where we've had arrows on these, make sure you include that because it means that it keeps going in that direction. I have a tendency to deduct if you don't include that because you have to show that the graph keeps going in that direction. Okay, so do that for linear and quadratic. Now, our interval notation here, we see that it's 0 to positive infinity because it starts at 0 here, but it doesn't go any further than that, and then the x, it just kind of keeps going in that direction. And then the range, it starts at 0, but it's just going to keep going up on the y part, hence 0 to infinity on there. So here's the corresponding inequality notation. So x is equal to, or 0 is less than or equal to x, and x is less than infinity, and then we have the same thing for our y. Our set notation, x is such that x is greater than 0, and y is such that y is greater than or equal to 0. Now, let's look at the general form here. F of x is equal to a, okay, so here we have an a here as well, and then we have a square root of x minus h quantity, and then a plus k. Okay, again, you're going to see this pattern in all of these equations, and we're going to talk about what that general form means a little bit later. So absolute value, that's our V looking thing. It's basically two different, kind of like two different lines with the same start point. And the parent function is y equals the absolute value of x. And our general form here, f of x is equal to a in front. And then inside the absolute value, x minus h. And then that quantity is being absolute value, is in the absolute value. And then again, plus k at the end. Okay, so start to see a pattern here. Interval notation. Okay, domain, negative infinity, positive infinity, range. So this one's really going to be exactly like the quadratic. So go ahead and you can pause it and copy that down, and I'm going to move on from here. Okay, now you don't have to know what a logarithm is yet. We'll go into great detail about that later, but just know that there's a logarithmic parent function, and it looks kind of like this. And it goes forever in this direction, and it goes forever in this direction. And we're going to say y is equal to the log of x. Okay. Now, just know that it exists, but also know a few other things about it. For instance, it's good to know that there is this part where it's kind of coming down. Here it's getting closer and closer to the y-axis. It's never going to touch the y-axis, and it's going to get there forever. It's going to get there closer and closer forever, but it's never going to get there. and we say that there's an invisible, on the y-axis in this case, there's this invisible line. It's we represent it with a dashed line, and we say that, move that over a little bit, that dashed line has a name, and it's called an asymptote. So it's an invisible line that's where our graph approaches but will never touch or cross. Okay, so we're going to go with that definition of an asymptote for now. We're going to modify it down the road, but just understand that general principle. You'll see it again here. Okay, so our interval notation here. So since it's approaching 0, the domain here, it gets closer and closer to 0 on the x, but it'll never reach it. We don't have the bracket. Note that we have parentheses. Okay, so take note of that. So we use parentheses instead of a bracket because it's never going to touch 0. And then it goes to infinity on the x. So it keeps going in that direction. Range, okay, forever down, forever up. And then the corresponding inequality notation. So x is going to be x is less than 0, but never going to equal it. X is less than infinity. And then, of course, y is going to be negative infinity, positive infinity. Our set notation, we're going to say x is such that x is greater than 0. Or, here's another way to write that. X is such that it is this... x is such that it is a set of all real numbers positive, or just a positive all real numbers. Okay, so that means it excludes 0 and negative numbers. 0 and negative numbers are not part of that because we only want positive real numbers. You can go back to that very first lesson if you don't remember what real numbers are, but basically it's all the numbers. So that's a shorter way to do that. And then here y, we say y is a such that it is a set of all real numbers. Okay. Oh, and sorry, let's look at this real quick. Log, the general form. Log, and you don't. We're not going to go into detail about it today, but just know that there's an a here. It's like a subscript, and then the log of x minus h is a quantity, and then again plus k at the end. What does it all mean? We'll see in a minute. Exponential. Okay, so the parent function is y equals 2x, and we have an asymptote. And the asymptote on here runs horizontally. Okay, and the general form on this guy is a as the base here. Okay, now a can be different numbers, as we can see here. So in this case it's 2 for the parent function. That's what we're using. And then x minus h together again, and again you see it's minus, and see that it's like the whole thing is in the exponent, and then plus k at the end again. Alright, so with this guy here, it's going forever ever to the left and forever and ever and ever to the right. So our domain is going to include all real numbers. So here's our corresponding domain in interval notation, inequality notation, and we see it here in our set notation. Since it's not going to touch the x-axis, it's not going to hit 0 on y. It's not going to include, so we use parentheses instead of a bracket in our interval notation, and then it's going forever to infinity. And then here is the inequality notation, and then we could say that in set notation y is such that y is greater than 0, or you could put it as y is such that it is a set of all positive real numbers. Okay, either way is fine by me, so we can go that way. Rational. Okay, this is the last of the parent functions that I need you to know. Now, rational actually has not one, but actually two asymptotes, one on the y-axis and one on the x-axis. Okay, it's got two branches to it. One in, do you remember what quadrant this is? It's quadrant 1, and then we have one in this quadrant, which would be quadrant what? 3. Okay, it goes 1, 2, 3, 4. It's important to know what quadrants your parent functions is going to be in the rational. Okay, 1 and 3. So you'll have to memorize that. Flashcards will be probably a good idea to help you memorize these and remember what how they work. Some sort of mnemonic. It's going to require some studying and looking at these over and over and over again. So the parent function for this is just 1 over x, 1 divided by x. Okay, and the general form here. So here we got an a up top. And then see how x is at the bottom here? Oh, no, you can't see it, but x is at the bottom here in our parent function. Well, x is in the bottom in our general form, but now there's that h, that minus h, all together in parentheses, and then plus k at the end. All right. So for this one, when we talk about the interval notation, see, it's not going to touch 0 on y or x, so there's going to be a little gap here. So our domain, it's like going from negative infinity to 0, but not including it. But then we're going to use this comma here, and then we're going to know, and then on the other branch, it's going from 0 to infinity. So we have to break it up into two parts. So we do the same thing for the range here. Down, forever and ever and ever, up to 0, but not including, and then from 0 up. Okay, and so forth. Now we use an OR statement. This is the only one that we use an OR statement on. So x is less than 0. So it's going to be less than 0 but not equal to, or it's going to be greater than 0. And then the y's, it's going to mirror that. Forever down or forever up, but skipping over 0. Set notation is going to look just like the inequality notation. But you could also do it this way. You could say that x is such that it is a set of all real numbers positive and negative, meaning all real numbers that are positive and negative. So what's excluded here? 0, because 0 is neither positive or negative. Okay. Let's talk about what that h and k stuff is talking about, and we're going to go into this real quick here. The changes of I'm going to talk about the changes of what that a value is. Okay, so we're going to look at the square root function here. Let's say our a is 1. There's an invisible 1 here. This is going to be our parent. So there's going to be no change to it. It's just going to, we're just sketching a graph. Doesn't have to be perfect. Later on, we'll be perfect about these. We'll plot, points. If it's negative 1. This is going to be a vertical reflection. Okay, meaning it's just going to reflect over the x-axis. Okay, when our a value is negative, so it's just going to do this little number here. Okay, so our parent will reflect. If we have whole numbers, numbers that are positive, larger than 1, we could say, this is going to be, I can't write, I'm going to erase this just so I have room to write here. We call this a vertical compression. Stretch. I'm sorry. In other words, it's going to be narrower or skinnier. Okay, that's hard to read, but that's narrower. So vertical stretch means like if it were we're going to be stretching it vertically. So in this case, if this were our parent function, let's say this is our parent function, then this one is going to be stretched vertically. It's going to be pulled up a bit more. Okay, it's just going to be higher up. And if it's going to be a fraction like 1/3, that's going to be a vertical compression. We also say it's going to be wider in some cases. I don't know. It's also called a vertical shrink. I'm going to try to refer to it as vertical compression, like you're squishing down on it vertically. So as kind of a comparison, here's my, let's say this is my parent function. All right, so this guy here is going to be squished down. It's not going to go up as fast. Okay. You're not going to see a lot of this. I just want you to know it's out there. This is when the x is negative on the inside versus the outside, like we see here. This is going to be a horizontal reflection. So it's just going to do this number instead. So it's going to reflect over the y. Now let's talk about that k value. So with the k, let's say our k value is 0. So if you're looking at that, you should be referring to the your general equations. Look back at those, help you follow along. So if it's 0, okay, so basically this is going to be our parent. Okay, there's not going to be anything going on here, and the parent function, we just saw that. That's just going to be your V shape, if you will. And if it's a negative, we're going to shift down. Okay, and so since it's a -4, that means we go and we count 1, 2, 3, 4, 1, 2, 3, 4, and our graph is going to just be shifted down 4. So our k is a vertical shift. So if I were to have a +4 here of my k value here at the, remember k is at the end, that's going to be a shift up. That's supposed to be up. So I count that out. 1, 2, 3, 4. So it's approximately going to be up. The vertex is going to be up in the air, like that. Okay. Now let's look at the h. So we'll do this in terms of a quadratic. So the parent of a quadratic. So we know that's just going to be a U shape. Now remember, all these, the h's and k's affect all the parents the same way. Okay, I'm just choosing one to show you how it works. So now this is interesting, because remember, with all of these, it's going to be x minus h, okay, as opposed to plus. So if h is 2, okay, it's like I'm saying x minus, and I'm plugging in a +2, that's telling me I'm going to be shifting to the right 2. Okay, so I just plug it in here, and so that means I'm going to go right 2. Okay, so we would just take our parabola and just shift it right 2. Even though in the equation you see a minus here, it's going to be the opposite because of the minus sign in the general equation. So in the case of if my h is a -2, it's going to look like this. It's going to be +2 because I'm plugging in a negative number. I'm substituting in a negative number for h. Okay, so thus that's going to become x plus 2, as we see here. So this is going to be left 2. So you'll be given the equation, so you'll have to see the plus sign saying, oh, well, it's originally minus, so in order to change it, it must have been a negative, so I have to go left 2. Okay, so that's your horizontal shifting. All right, so let's do a couple examples. Let's start putting everything together. All right, so here let's look at a quadratic, and we have f of x equals x squared. Here's that general equation, ax minus h squared plus k. So now we're going to plug in numbers. So we're going to be doing some transformations. I have f of x equals 3, and then x plus 2 squared minus 1. All right, so we're going to write down what these values are. So a is 3, h, so because that's a plus sign, that means we had to plug in a negative 2, because remember that was originally a minus, so we had a negative change signs, and then our k is going to be a minus 1. So we're going to write down all the shifting that we're going to be doing. So this is, first off, that's a 3, that's a number larger than 1. So it's a vertical stretch. We're also going to have a, we're going to shift left 2, and then we're going to shift down 1. So we'll start off, we know, I want you to just lightly sketch the parent function on here, because I want you to have a frame of reference. So just do that. Okay, there's the quadratic parent function. Okay, so for this new one, we're gonna use the vertex here as our frame of reference. That's going to be hk. Okay, our h and k will tell us where the vertex is. So we're going to left 2 and down 1. So our new vertex is located here at -2, +1. And since this is a vertical stretch, we're stretching it, we're going to be making it skinnier, narrower. How much narrower? We're just going to sketch it so that, we're just going to do something like this. Does that look narrower than the parent? Yeah, sure, it does. Okay, that's good enough for our purposes. Okay, now, so real quick, let's look at the domain and range and the different notations for this. So the domain on this guy, on our child function, so after the parent has been translated and transformed, it's called a child function. So we're going to look at this red child function. So the domain on this guy here is still going to be the same. It's going to be -infinity to +infinity. And the range, though, it doesn't go down to 0, it goes down to -1. And since it actually includes -1, we do it like that. So the inequality notation here is going to be, we'll say that, well, it's going to be between -infinity, so x, so -infinity is less than, but not equal to, x, and x is less than +infinity. For this one, the range, we'll just say -1 is less than or equal to y, and y is less than infinity. Set notation, x is such that x is in the set of all real numbers. And for our range, y is such that y is greater than or equal to -1. Okay. Okay, for this next one, I'd like you to try this next one on your own. So go ahead and pause the video and work it out. And then once you got it, resume it, and then you can see what it looks like. Pause in 3, 2, 1. And there you go. So take a moment and look over that. And we'll do one more. Okay, so this is the last one we'll do, reciprocal function. go ahead, pause your video one more time and see if you can do this one on your own. You can pause in 3, 2, 1. Okay, so I have to apologize real quick here. Here it said vertex. We're not really using a vertex when we translate this. We're going to use the center, that's the origin, and we're going to be using that as our spot. So we go right to up 5, so that would be right to up 5. And what I do is I use I draw on the asymptotes to help guide where the graph is going to be. So it's going to be here and here, and you just kind of get that in there as best you can without actually crossing the asymptotes. So if you need to go back and correct your domain and range, go ahead and do so, and pause, and 3, 2, 1. Okay, here are your domain and ranges. Take note with inequality notation, you can write it this way, or you could do it more simply like this. For x, you could just say x is not equal to 2. That's a shorter way of doing it. And for y, you could also just say y is not equal to 5, which is what I've done for the set notation as well. So you might prefer doing it that way. Anyway, that is parent functions and their transformations. There'll be there'll be some questions for you to answer in the secret questions that are in your notes